Okay, so now let's look at some example problems for sampling proportions. Um, so let's say, so in the fall of 2008, there were 18,516 students enrolled at California Polytechnic State University in San Luis Obispo. So, okay, so of those students, 8,091 were female. So, like, if we were looking for the probability um, that someone is female, okay, um, we're going to sit here and see that we have the number of females, which is going to be 8,091 over 18,516. And so our proportion there is going to be 0.437 or 43.7%. And if we were looking for, so this is the probability of being a female. So the probability of being a male then, let's say, if they asked us that question, we would need to figure out, so the rest of the students would be deemed male. So we're going to be looking at, let's see, 10,425 out of 18,516, which based off of this math, you should get 563. And if it needs to round, that can happen too. May round to be something a little different, but it would follow that that has to be true. So if you're looking just for a proportion, if it gives you numbers, you just need to divide them and find them on your own. Now, a different problem here. So let's say we have an article, unmarried couples more likely to be interracial. It says that 7% of married couples in the United States are mixed racially or ethnically. Consider this population of all married couples in the United States. So we're going to talk about all of these. So A says a random sample of 100 couples will be selected from the population, and P hat, the proportion of couples that are mixed racially or ethnically, will be computed. What are the mean and standard deviation of the sampling distribution P hat? So if we're looking for this, so A, so the mean for P hat, okay, that okay, the mean for P hat is the same thing as P, so that's going to be 7%, which is 0.07. And our standard deviation for P hat, that follows the formula where we do the square root of P times 1 minus P over N. So we just need to replace these things. So P is 0.07. 1 minus P is 0.93. And N is 100. So, sorry. So that right there, so we need to go ahead and find this information. So we're going to do the square root of the numerator is going to be 0.07 times 0.93. And then we're going to divide that by 100. So you should get 0.0255. 0.0255. So we get B says, is it reasonable to assume that the sampling distribution of p hat is approximately normal for random samples of size n equals 100? So that means we need to have n times p to be greater than 10 and n times 1 minus p to also be greater than or equal to 10. Well, n is 100, p is 0.07, and that equals 7. Well, this is not greater, 7 is not greater than 10. So we can already say that this is not going to work. Now if you did the other way, 100 times 0.93, that equals 93. That's bigger than it, but we need both. So no. Not reasonable. So C says Suppose that the sample size is 200 rather than n equals 100. Does this change the size of, change the mean or the standard deviation? If so, what are the new values? So the mean does not change. It will still be 0.07, but our standard deviation will change. That's going to be the square root of 0.07 times 0.93 over 200. And so we can go back and figure this out again. I'm just going to repeat a previous entry. I'm just going to change the bottom to 200. And so this is going to be 0.1804. Or, excuse me, 0.0180. So that is our new standard deviation. It got smaller because our sample size was larger, and that's what we've learned so far. The larger our sample size, the closer our distribution is going to be towards the mean. So a smaller standard deviation is expected there. And D asks us here, is it reasonable to assume that the sampling distribution of p hat is approximately normal for n equals 100? So, or equals 200. So we say n times p has to be greater than or equal to 10, and n times 1 minus p has to be greater than or equal to 10. So we have 200 times 0.07. That is going to equal 14, and n, which is 200, times 0.93, that should be 186. So yes, it is reasonable. And that is because both 14 and 186 are greater than equal to 10. So we're good there. It says, finally, when n equals 200, what is the probability that the proportion of couples in the sample who are racially or ethnically mixed will be greater than 0.10? So we can use the normal distribution now. And so we have to use all our information that is based off of a sample size of 200. So since we can use the normal distribution, we're going to say normal CDF. Okay, it says going to be greater than 0.1. So we have 0.1. We have our standard deviation is 0.018. Our mean is 0.07, and our standard deviation is, oh, excuse me, I apologize. It should be 1, or 1e to the 99, whatever you would like. It just needs to be reasonably large because it's the upper bound. This is my fault. And then we do 0.0180, and then this should give us our answer. So when you go and plug this in, you go to second distribute using normal CDF. So our low bound is 0.1 because we're doing at least 10%. Our upper value we'll do is 1e to the 99, just because that's the highest number our calculator can do. And we'll do 0.07 for our mean, and our standard deviation is 0.0180, and find our answer, and this is 0.0478. That's the same thing as 4.78%. So if we were to create a sample size of 200, the chance that we got more than 10% of those couples being mixed racially is only about 4%. Now, we're getting that information because we have a large enough sample size in order to assume that it's going to be normally distributed. We found the area of our curve to the right of 10%, which represents all the samples where we would have more than 10% occur, but that only represents about 4%, about 5% of the area of the entire thing. So this is a pretty small percentage.